Okay, so this is going to be the third video in section 4.1. I mentioned 4.1, 4.2, but we haven't really begun 4.2 yet. Subspaces, vector spaces are pretty much just captured all in 4.1. However, there's a little bit of carryover into 4.2, so let me go ahead and finish up the last bit of material that I want you to know before we start moving on to some different material. So in the last two videos, what we did was I first introduced the idea of a vector space definitionally, the idea of a subspace definitionally. I tried to capture what a vector space and a subspace would look like within the analogy of Netflix. And then we began with subspaces, because subspaces, there was only three axioms that we needed to verify in order to make a statement that that H was a subspace of vector space V. So now we've circled back to vector spaces, and I'm not going to. We're going to practice a little bit with vector spaces. I'm not going to go through and verify all 10 axioms. But again, maybe it's been a while since you watched those first two videos, so let's recap. So what is a vector space, right? It's a set of vectors, right? It can't be an empty set. It has to be a set of vectors. Does not matter what type of vectors are in this set. They can be vectors in R2, vectors in R3, vectors in R1, but it is a set of vectors. And a set of scalars of which there are only two operations allowed. Okay? Remember, the only two operations allowed are vector addition and scalar multiplication. Now, in the following case, you have because you have to think of it like you are in essence looking at this as a system, okay? And all 10 of these axioms must hold in order for it to carry the name of a vector space. So the axioms must hold for what they define it as vectors u, v, and w in V, and for all scalars c and d. Now, all I'm going to do really quickly, I'm not going to actually go through this, but take, for example, the set of vectors in R1, right? So if the set of vectors in R1, this would simply be a line, right? We're dealing with numbers on a line. And what would each vector look like in R1? Just think about vectors are always n by 1, right? They're always n by 1 matrices. So if you are in R1, let me go ahead and build this would be my vector. And if we're in R1, how many entries would we have here? Well, we just have one, right? We just have x. So what would the vector space of R1 look like? Well, it would be the set of vectors. Okay? And now if you wanted to show that R1, right, one-dimensional space does meet all 10 axioms, you would begin by what I have off to the left here. You would begin by listing, you would need 3 vectors, 2 scalars, and you would then proceed to show that each axiom holds. Okay? So we're going to make it a little bit easier than that. That you can see how that would be time consuming. It's time consuming just verifying subspaces, and there's only 3 axioms in the subspaces. So let's see if we can let's see if we can start with the following example. So it says, is V a vector space? All right, now how do we read this? So V is the set of vectors such that x is greater than or equal to 0 and y is greater than or equal to 0. All right, so we have this the vectors. It appears that if we take a look at our vectors, our vector is a 2 by 1. So if it's a 2 by 1, we are in R2 space. And now let's first draw the vector space. Okay, so the set of vectors such that x is greater than or equal to 0 and y is greater than or equal to 0. So you can see that the geometry of where we are. So over in quadrant 1, this is where all positive, my apologies here, drew x twice. If you're in R1, all your x values are positive. I'm sorry, if you're in quadrant 1, all your x values are positive, all of your y values are positive. And of course we are saying all x values must be greater than or equal to 0. All y values must be greater than or equal to 0. So this is the geometry of what we're dealing with. Okay. Now, the question is it a vector space? Okay. So I agree, this is quite daunting because there are quite a number of axioms to go through. That you would have to, and we'd have to make sure that this V satisfies all 10 axioms. I'm going to cheat a little bit, okay? So for example, I'm going to let V, again, just be some vector in that vector space. And then remember, if to say it was closed under scalar multiplication, right? Remember the axiom that was closure under scalar multiplication. What, if you recall, what did that mean? So the idea was, so for any vector you choose in your vector space, please don't let me lose you yet. That just means if I reach over here in quadrant 1 and I grab a single point, a single vector, okay, and this was going to hold for any vector that I grab, but let's assume that I grab some single vector. Now, what I should be able to do is multiply that vector by any scalar, c, which, okay, c is going to be real numbers, so negatives, positives, 0. I should be able to scale that vector, and what should come back out should also be in that same vector space. That's what it means to have closure under scalar multiplication. So again, I'm going to cheat a little bit. So I'm going to choose a scalar of -1. Okay? So let's do some math here. So I've chosen -1 for C, and I've chosen x, y for V. And let's go ahead and see what comes back out. This would be -x, -y. Now, what comes back out should also be in the shaded region, right? Is it? Well, -x, -y, that's in quadrant 3. Right, here's where the x's are negative and the y's are negative. Do you understand that you don't have closure under multiplication? So therefore, is the following V a vector space? The answer is no. If you can show that it doesn't satisfy one of the axioms, then you have satisfied that it is not a vector space. Okay. Let's continue. Ready? So we're asked the same question. Is V a vector space? Well, let's read how they've defined V. So V is the set of vectors in R2 such that x multiplied by y has to be greater than or equal to 0. In other words, every time you take x times y, you should always get a positive number. You should never get a negative number. So now, what is the geometry of that? Well, I think you'll agree with me. Quadrant 1, the x values are positive, the y values are positive. In quadrant 3, the x values are negative, the y values are negative. So what we have in this case is the only way you're going to get a positive number when you multiply the x times the y is if you choose from those two quadrants, right? A positive times a positive is going to be a positive number. So this is part of your vector space. A negative times a negative is also a positive number. So this is part of your vector space. And now the question becomes, can we show that this is a vector space? All right. Well, again, it can be daunting because we have 10 axioms to deal with. In this case, what I'm going to do is sometimes we can get lucky, and we can start with, say, well, I tell you, the best place to start is the zero vector. Because if the zero vector is not in your shaded region, then you can automatically rule out that it's not a vector space. But so in this case, this includes greater than or equal to 0. So the zero vector is part of this vector space. So okay, so far it's looking like it might be a vector space. So now at this stage, let's look at the idea of closure under vector addition. Okay, and here's one more shot to make sure you understand what closure under vector addition means. So that means that for any two vectors you choose, so let's say u and let's say v. Now what did I just say? I said if you reach into these shaded regions and you grab two vectors, okay, any two vectors, then to have the property of closure under addition would mean that when you add those two vectors, what comes back out must also be in the shaded region. Okay? So it must also be in V. Now, as I mentioned, this is not always a good this is not a good strategy to just randomly choose points in the shaded region. Unless you've started to practice a little bit, and you can, once you've practiced these techniques enough, you start to kind of notice things, and you're welcome to always try, okay? So, for example, I'm going to choose vector 1, 2, and I'm going to choose vector -3, -1. Okay? Now, first, let's you and I agree that if vector u over 1 up 2, that is in the shaded region, that's actually in quadrant 1. Vector v, if we moved to the left 3 down 1, that is in quadrant 3, that is also in the shaded region, vector space v. So the question now becomes, what happens when I add u plus v? All right, well, u plus v would be 1, 2 plus -3, -1. And what do we get back out? Well, -3 plus 1, that's -2. And 2 minus 1 is 1. Now the question is u plus v in the shaded region? Well, clearly not, right? If you were to plot the vector -2, 1, we would go, say, to the left 2, up 1. You understand that we would be here in quadrant 2. Now, I have already shown with that one example shows that V is not a vector space. But what if you chose 2 points? You did this arithmetic that I did, and you ended up with a point that was in V. What conclusion can you draw? None. What if you did this 10 times, and every time you did it, you kept showing that you were getting points in the region? What can you conclude? Nothing. You cannot show by just choosing points, right? You would have an infinite amount of summation to do to be able to make this statement. So normally what you have to do is you have to use generic points, right? Like x sub 1, y sub 1, x sub 2, y sub 2. So you have to normally what you have to do is use generic points and then kind of massage your way to see if you can make a statement about u plus v. But the beauty is, if you can just find a single instance, like we did, where it does not close under vector addition, that single instance is enough to throw away the hypothesis. It's enough to disprove that it is or answered the question as to whether it is not or is a vector space. All right, let's try another one. Now, so vector spaces, I want you to understand, vector spaces are much more abstract than systems in R1, R2, R3, R4, things like this. You don't need a coordinate system at all, actually. I could give you a polynomial and ask you, is it a vector space? I could give you a bunch of arrows and ask you, is it a vector space? The idea is, though, it's much easier to see if we stay in some type of coordinate system, so we're going to continue in our coordinate system. The question now reads, is the line that is through the points 1, 1 and 2, 3 a vector space? Now, I've already cheated here a little bit. I've already plotted 1, 1, and plotted 2, 3. And I've drawn my line. But what I'm going to do is, I'm not going to cheat right now. I'm going to erase this line and simply go back to my points. Okay? So 1, 1, and 2, my apologies, I hope I can get this. I think we're right here, 2, 3. All right, so, okay, wow, that's interesting. So all you're given is 2 points, but you're asked about the line that goes through the 2 points. Is that line a vector space? Interesting. Okay, so how do we proceed? Well, first I'd like to be able to graph that line that we are considering. And that's fairly easy to do. If I just label, say, x sub 1, y sub 1, x sub 2, y sub 2, then you know how this works. If I just simply place them into my point slope formula, and then I would be able to solve for y, and I would be able to graph. But of course, what am I missing? Now, obviously, I'm missing the slope, right? I'm missing the slope of that line. But that's not that bad either. The slope is just simply going to be 3 minus 1 over 2 minus 1. So I have 2 over 1, or just 2. All right, so with this slope, and I really only need one of those points now, I'm going to be able to form the equation of the line. And what does that look like? It should look like this. Y is equal to 2x minus 1. Okay. So what is the vector space that you are considering? Well, it is the line drawn by the equation 2x minus 1. Now, if the first thing that we should do is you should let me pretend like if this were the problem that I was given. I'm going to start with the harder way of showing that this is not a vector space. And then I'm going to come back to something I said just a few minutes ago, that where I always start is the zero vector. So, but I'm going to assume that I have forgotten my own advice. So how might this work? Well, let's take u. That's going to be a single point on that line. I'm going to let u be 1, 1. And then I'm going to take v, which is another point on that line. Doesn't matter what point. I'm going to choose 2, 3. Okay. And now, to say that it has closure under addition would mean that u plus v must also be on that line. Right? So u plus v must also be on the line of y equals 2x minus 1. So what is u plus v? Well, 1 plus 2 is 3, and 1 plus 3 is 4. Now the question is u plus v on the line drawn by y equals 2x minus 1? Well, you want to know how to do this? Well, very simple. If we plug 3 in for x and we plug 4 in for y, do we get a true statement? Well, here we go. So this would be 4 is equal to 2 multiplied by 3 minus 1, right? So that would be 4 is equal to 6 minus 1 is 5. Notice that we end up with a statement that is not true, right? 4 does not equal 5. So as of right now, I have enough information to say no, this is not a vector space. But can anyone spot an easier way? And I've already said it. It's the idea of the 0 vector. That means that line, if you draw that line, it has to go through the origin. Does y equals 2x minus 1 go through the origin? Well, that would mean when x is 0, y is 0, right? So if x is 0 and y is 0, you end up with a statement that 0 is equal to -1. That right there is enough to show that the line does not go through the origin, right? Just when I drew it a second ago, I tried, a little bit sloppy. You couldn't really show that it wasn't, it didn't actually go through the origin. So that's why I erased the line. But if you draw it, that line does not go through the origin. Therefore, no, this is not a vector space. All right, so I want to recap. I do have a few other things I want to tell you, but I thought I would be able to do all this in one video, but I think it's probably best to do this in 2 more videos. So I'm going to stop here and pick back up in just a second.